as well. Thank you.
Okay. So first, I want to thank the organizers for letting me to give this talk. So about completeness of quantum circuits. So this is a joint work with Alexandre Clément, who is doing a PhD here in Nancy. I think he's here around. And also Nicolas Hurtel, who is doing a PhD with Shane Mansfield at Candela and Benoît Valiron at Quarks in Saclay. Okay, so I think I can be brief on the motivations because you probably all know that quantum circuits is ubiquitous in quantum computing. So we use quantum circuits for lots of things. So for instance, for describing quantum algorithms. If you have a look to Wikipedia, you will see that there are quantum circuits for describing Shor's algorithms or Grover's algorithm. And so for this high-level description of quantum algorithms, we use quantum circuits, if it makes sense to say something like this. But quantum circuits is also very important, even if you use some modern quantum programming languages. You can use this language to write a program, but it turns out that if you run this program, at the end of the day, what you get is a quantum circuit, because most of the modern quantum programming languages are just languages for quantum circuit description. So you can describe small circuits like this one, more elaborated circuits, bigger circuits, or even bigger circuits, right, using these languages. But at some point, you have a quantum circuit. Okay, so it's at least used for intermediate language, but also in other aspects of quantum computing. Okay, so as I said, it's ubiquitous in quantum computing, and once you have a quantum circuit, especially if it has been generated automatically, like in the previous examples, you may want to transform this circuit, okay, to optimize the resources, for instance, decrease the number of gates or decrease some particular gates, 2-qubit gates, T gates, if you want to make it fault tolerant. So, okay, you may want to do these kind of things. You may want to satisfy some hardware constraints. So for instance, here we have an example where we have in the memory some particular constraints. So the 2-qubit gate should be applied in some particular places. So, okay, so you want to transform your initial circuits in order to implement it on these particular quantum computers. You may want to make it fault tolerant. So somehow it's, so here the idea is that you also want to keep the same semantics. So to implement the same algorithm, but now you want to add some extra gates, some redundancy in order to make it fault tolerant. And finally, the most general case is when you want to reason on quantum circuits and show that two circuits are equivalent, for instance, to show that a circuit is satisfying some specification. Okay, so for all these applications that you already know, we need circuit transformation. We need a way to transform a circuit. And a simple way to do this, and a natural way to do this, is to use an equational theory. That is some equations saying that we can replace a piece of circuit by an equivalent piece of circuit. So here you have 4 examples of such equations on circuits. And well, this is a way to transform a circuit and simplify it maybe. And you know that when we have an equational theory, the ground, really the property that you want is to have a complete set of equations, which means that if you take 2 circuits which are representing the same unitary transformation, then you are able to go from one circuit to the other one just by using the equations of your set, of your equational theory. Okay, so that's the objective, the topic of this presentation, to find a complete equational theory for quantum circuits. Okay, so what do we know about completeness in quantum circuits? So we have a few results. So the state of the art is the following. So first of all, we have this nice result by Peter Selinger and Xiaoning Bian, which is a result for a completeness result for 2-qubit circuits. So only circuits acting on 2 qubits. And moreover, it's for the Clifford plus T fragment. So using Clifford plus T, it's actually, it's probably more difficult than using the entire space, but this result is for this particular fragment. And they have introduced a nice equational theory, which is complete for this fragment, made of 20 equations. Here I'm presenting just three of them, and you see that these equations are already involved. Okay, there are non-trivial equations for this particular fragment, acting just on 2 qubits. There are other results. So, for instance, for the stabilizer fragment or Clifford fragment by André Ranchin and Bob Kuke, based on the ZX calculus, if I remember well. But it's for quantum circuits, Clifford quantum circuits. And there is also this result for a C0 dihedral fragment, that is when you have C0, X, T, but no Hadamard. Okay, in this fragment, it's important that there is no Hadamard, no creation of superposition. So this is a result by Mathieu Ami et al. Okay, so we have this result. So this is for fragments of quantum circuits, non-universal fragments. And what is interesting is that there are also results for generalization of quantum circuits. And here I'm talking about ZX calculus. So we know that it's complete. We have complete axiomatization for ZX calculus, for Clifford plus T, for the general quantum ZX calculus. And this is interesting because ZX calculus is a generalization of quantum circuits. So it means that we can represent quantum circuits. This is the circuit-like ZX diagrams. And here I'm representing, so for a given unitary transformation, I'm representing all the possible ZX diagrams representing these unitary transformations. And we see that some of them are circuit-like. This is the red part. And others are not necessarily circuit-like. Like this one here, it's the shape is not, we cannot recognize immediately a quantum circuit here. And okay, so quantum circuit, so ZX calculus is a complete. But so what does it mean? It means that if we take 2 quantum circuits, so 2 circuit-like ZX diagrams, there exists a way to transform one into the other, but maybe the path going from one to the other is using non-circuit-like ZX diagrams. And in practice, this is what's happening. And the point is that because of this, it's not easy to derive from the completeness of the ZX calculus a completeness for quantum circuits, because we want to stay inside this red part. And I don't really know how to push this element and stay in this red part. So I've tried, but I didn't succeed. So maybe there is a way, but at the moment, I don't know how to do this. And we cannot derive a completeness result for quantum circuits using ZX calculus at the moment, at least. So this is the picture for ZX calculus. So there are other graphical languages, ZW, ZH. They are all proved to be complete now. And but this is a very similar situation. Okay, we don't know how to derive a completeness result for quantum circuits using these languages. And okay, so but today the main result I want to show you is actually a complete equational theory for quantum circuits. And the idea is that we will not use these languages I've talked about, but another one, the Love calculus, which is a language for optical quantum computing. So it's okay. So from now, I'm going to for the next slides, I'm going to talk about this language, the Love calculus. Okay, so it's a language for linear optical quantum computing. So really, the idea is to represent optical quantum computing using really primitives as they are used by a physicist when they want to describe such an experiment. So we have a phase shifter, we have beam splitters, we have polarizing beam splitters, generators, detectors, these kind of things. And we put them together. So here the wires are representing intuitively the possible path of a photon. So optical fibers, if you like, or similar things. And so we have this graphical language And we have proved some interesting properties about these languages. But for today, for this particular talk, we will actually restrict our attention to a fragment of this language, which is the polarization preserving case. So we will not take into account the polarization of the photons, and also the single photon case. We consider that there is only a single photon in the circuit. So what is this fragment? So at the end of the day, in this fragment is just a prop, which is generated by two generators. So the beam splitter, which is here, and the phase shifter. So the beam splitter, it works like this. So when you have a photon here for this input, it's either reflected or transmitted. So with some amplitude, it's reflected and you get your photon here, or it's transmitted with this amplitude. So this gate is perfectly symmetric. So if the photon is now inputting the device with this wire, you get something similar. Okay, so this is the polarizing beam splitter. So the beam splitter, sorry, which is parameterized by an angle theta, right? And there is also the phase shifter. So this one, you have one photon as an input, one photon output, and just a phase when the photon goes through this gate. So it can be represented, so the semantics can be represented using matrices. So here it's just this rotation here for the beam splitter, and here phase shifter is just a multiplication by this phase. So once you have these generators, you can compose them. So sequential composition is the usual composition, and parallel composition is the direct sum. So here it's an important point, because if you compare to quantum circuits, in quantum circuits, when you do the parallel composition, you get a tensor product. Here it's a direct sum. So it's a fundamental difference between quantum circuits, but also ZX diagrams and so on one side, and this language on the other side, because we have here a direct sum. Okay, so by construction, when you have such an optical circuit, if you look at the semantics, you get a unitary transformation. A unitary transformation acting of dimension n being the number of wires of the circuit. Okay, so we have this language, an interesting property which has been
sorry, Simon.
Yes. Yeah.
Can you go back to the previous slide?
Yes, sure.
So you called this fragment the single photon fragment, right?
Yes.
So what if you have like n wires, what does that represent physically?
So if you have n wires, it means that you have n possibilities, n possible inputs. So you choose where you put your photon. You can put it on the first wire, second wire, and so on. But you will always enter just one photon, but you can choose where you put your photon. And you can also put, so you may have a single photon in superposition of different positions. And in this case, you have a superposition of inputs, but always a single photon. Might be in superposition, but always a single photon for today. Okay.
Thanks.
Okay, so there is this result in the 90s. A universality result. So for any unitary transformation, there exists a circuit of that shape, this triangular shape, which is implementing the unitary transformation. So the star means that you have some value of the parameters which are implementing the unitary transformation you want. Okay, so it's a universal model. You can implement any unitary transformation, and we have this interesting triangular shape form. Notice that this form is not unique in the sense that if you want to implement your favorite unitary transformation, there might be several values of the angles such that you get the unitary transformation you want. Okay, so the angles are not unique in this representation. I will go back to this point in a few slides, but we have this interesting universality result. Okay, so what we have introduced with Alexandre, Nicolas, Shane, and Benoit is a complete equational theory for this fragment. which is fairly simple. There are 7 rules, which are simple rules, I would say. This equational theory is complete. So if we look at the rules, we can see that some of them are trivial. A, B, D are really trivial properties. E is a commutation property between beam splitters and phase shifters, a trivial one. C is a decomposition of the swap. So you can always decompose a swap using beam splitters and phase shifters. And we have 2 more elaborated, more complicated equations, F and G. So here you can see that you have several different angles. So it means that for any values of the angles on the left, there exists a value of the angles on the right such that the equation is true. Okay, so it's really a Euler kind of equation. And actually F is actually nothing but the Euler decomposition. You can interpret beam splitters as X rotations and here as Z rotation. And so you have X, Z, X equals Z, X, Z. And G is also a kind of Euler decomposition, but in 3 dimensions now. And again, for any values of the parameters on the left, you get parameters on the right such that the equation is true. Okay, so we have this equational theory, and this equational theory is complete. So let me show you briefly how we proved this. So first, we slightly changed the equational theory. So we start with this equational theory, which is fairly simple. We make it a little bit more complicated. And we consider this one, which is equivalent to the previous one. Okay, it's just that, well, we have some more equations, but well, it's equivalent. And once we have this, we actually turn this equational theory into a rewriting system. Okay, for all these equations, we consider that the left part is going to be rewritten in the right part. Whenever we see a diagram like, I don't know, like this one, we replace it by this one. And it turns out that this rewriting system has all the good properties we want. So first of all, it's sound. That is, it preserves the semantics by constructions, or it's easy to double check it. It's terminating, which means that if you start with any circuit and you apply these rules, at some point you will stop and reach a circuit on which there is no rule applicable. You cannot transform the circuit anymore. And finally, it's confluent, which means that there are potentially several possible paths. So it's non-deterministic, if you like, but you can always close this path. Okay, we always have this diamond property. We can always close and get a single circuit at the end of the day. So maybe just a word about this. So for proving termination, we associate a quantity to each circuit, and we show that when we apply the transformation, the rewriting rules, this quantity is decreasing. And since it's a non-negative property, at some point it should end, because it's strictly decreasing when we apply the transformation. So this is the way we prove termination. And then confluence, if we have termination, it's enough to show local confluence. So that means just one step here and there, and then try to close the diamond. And then to do this, we consider what is called critical pairs, that is diagrams where you have 2 possible derivations and show that that you can always close these derivations. Okay, so that's the idea. And we get a rewriting system which is terminating and confluent. Okay, so as I said, it's terminating and confluent. So it means that when we start with a quantum circuit, we end up with a circuit on which we cannot apply any transformation. And this circuit is of that shape. That is, we recover this universal form by Reck et al. As the normal forms of our rewriting system. But actually, we can be a little bit more precise than Reck et al. We can show actually that here we have, in the normal form, we have this shape, and moreover, we have some structure, which is represented like this. So what does it mean? It means that when we have a 0 somewhere for a beam splitter, so For instance, here, whenever you have a 0 here, you necessarily have 0 on as a cascade here on the diagonal here. All the beam splitters and all the phase shifters, which are on this part of the diagram, must be 0. Okay, so if you have a 0 on phase shift, it doesn't imply anything special. But if you have a 0 on the beam splitter, you have this structure. Okay, and this extra property guarantees actually the unicity, the uniqueness of the representation of a unitary transformation using these quantum circuits, these optical circuits. So now, with this extra property, for any unitary transformation, there exists a unique normal form with this extra property, which is representing U. Okay, so that's the property of the normal form, and actually we have enough properties to show the completeness. So how does it work? So we start with two optical circuits representing the same unitary transformation. So C1 and C2. We can apply the rewriting rules until we reach C1 prime and C2 prime, which are in normal form. So they are of that shape, C1 prime and C2 prime. So the rewriting rules are preserving the semantics. And since we start with the same semantics, it means that these two circuits in normal form have the same semantics. So thanks to this theorem, it means that these two circuits are actually the same. C1 prime and C2 prime are equal. So we have a single circuit here. And so now we have the path from C1 to C2. Okay, we have this path proving the completeness of the equational theory. Okay, is there any question on this before I move to quantum circuits?
So on the previous slide, so the directed rewrite rules you use. Mm-hmm. So is the idea here is you're moving beam splitters always up, and if there's two adjacent on the same line, it's like with the phi 1 and phi 2 and the theta 1, theta 2. So like it sort of fuses two beam splitters next to each other. Like, so you're sort of always moving phases upwards. That's sort of the idea here, I guess, right? Upwards and to the right.
So the phases you are talking about, yes, the phase shifter. Yes, we move it to the right, definitely. And for the beam splitters, we are putting them down, right? This is the last rule. So if you have a pair, you put here the number of beam splitter is not decreasing, but the idea is, so for the termination, for instance, we give a weight to each beam splitter, and if the beam splitter is on a wire on the top of the circuit, then it's heavier. The weight is bigger, right? Such a way that this diagram is larger than this one, according to the measure we use for termination. Okay, so this is how we push the beam splitter down, and we get this triangular shape at the end of the day.
Thanks.
Okay, so now I'm moving to quantum circuits. So we use a standard definition of quantum circuits. So we see it as a prop generated by the usual Hadamard phase gate. So here, this phase gate is just a Z rotation. We are not saying that it's a Z rotation because there is always this global phase, and we keep Z rotation for the other one. And so we call it a phase, but it's what you have in mind, and the C0 gate. Okay, we also had the global phase because we want to take into account the global phase. You can just ignore global phase if you don't like global phase, but here the language is designed in such a way that we can deal with global phases. So usual definition for these generators, and we see it as a prop, so it means that we can deform quantum circuits. Okay. So standard definitions for quantum circuits, and so what is and now what we want to do is to introduce a complete equational theory for quantum circuits. And here the idea is to use optical circuits as follows. So here is the general picture. So we start with two quantum circuits, CA and CB, with the same semantics, the same unitary transformation. And we will use optical circuits. So we will encode these two quantum circuits into optical circuits. So we'll see how to do this, but at least intuitively it's possible because it's universal. Optical circuits are universal. So at least there are circuits representing the same unitary as the quantum circuit we start with. So we use this encoding, transforming the two quantum circuits into two optical circuits. And then, we'll see that the encoding is preserving the semantics. So now we have these two optical circuits. We know there exists a derivation by completeness of optical circuits. We know that we can go from one to the other. And now what we want to do is to lift this proof to the quantum circuit case. And in order to do that, we use a decoding, that is a way to transform optical circuits into quantum circuits in such a way that we have the intermediate step of the proofs. Intermediate steps of the proof, sorry. So we know that, so we want to go through these circuits, and what is missing is just find the equations in such that we can fill the intermediate steps of this proof. Okay, so intuitively, the idea is that each time we apply an axiom of optical circuits here, we consider the decoded version of this axiom, and we will add enough equation to the quantum circuit model in order to be able to mimic, to simulate this equation here, this single equation by maybe several steps, but in the quantum circuit. Okay, so that's the general idea. And now I'm going to present the encoding and decoding we are using for this proof. Okay, so the encoding is, I think, intuitive. So if we start with, for instance, a quantum circuit, which is just the identity, and we want to encode it. So this is acting on 2 qubits, on 1 qubit, sorry, so on a system of dimension 2. So in terms of optical circuits, we will get two wires, 2 modes. One wire is representing ket0, the other one ket1. And the identity, the quantum circuit identity on 1 qubit is going to be these this identity on two wires, 2 modes, in terms of optical circuits. If we want to encode the phase gate, and so on ket0, it does nothing. On ket1, we apply the phase, so we get this optical circuit. And the C0, so the C0, we know that that C0 consists in transforming ket10 into ket11, and the other way around. So in terms of optical circuit, it's just a swap between these 2 basis states. Okay, so that's the intuition of the encoding. And if we look at this example, so which is the identity in parallel with this phase gate. So if we look at the basis states, if the basis state is 0, 0, we do nothing. Okay, so this is the first case. If the basis state is 1, 0, we do nothing as well. So this is this one. And we apply a phase for 0, 1 and 1, 1. Okay, so we get this optical circuit for implementing this, this quantum circuit. So, okay, so it's intuitive. I think, I hope it is. But actually, this is an interesting example because here, what we get is a circuit. So we start with a circuit, which is the parallel composition of the identity and the phase gate. But what we get here is not the parallel composition of the encoding of the identity and the encoding of the phase gate. Okay, the encoding of the identity is here, the encoding of phase gate is here, and here it's clearly not the parallel composition. Okay, even up to a permutation of the wires or something like this, because here, if we do the parallel composition of this and this, we have just 1 phase gate. Here we have 2 phase gates. Okay. And more generally, if we consider a 3-qubit circuit, we will have a number of wires, which is not the appropriate one if we want to do a parallel composition of the encodings. So here, clearly, the encoding does not preserve the parallel composition. So, which means that, so this encoding is not a monoidal functor. Okay, so, and this is a problem because it does not preserve the structure of prop. So it's a technical problem. I will not go to too much details about this, but actually we cannot use props for this. We have to go to a formalism with less structure, less equations, and actually we use bare circuits, that is really circuits that you can define using generators, and then you freely compose them with a parallel composition and sequential composition. You have no equation a priori, and you work with these bare circuits, okay? And you do all the proofs with these bare circuits. And okay, so I will not go to these details, okay? I will hide it. But if you go and have a look to the paper, you will see that we are using these bare circuits, which make it more technical. Okay, so intuitively, what we do in order to go around this problem of the parallelization, the fact that the tensor product and so the parallel composition is not the same in both formalism. The idea is that we use sequentialization. That is, we will really do the encoding slide by slide by sequentializing the circuits. That is, we will consider when we have a non-trivial generator, we'll assume that we have only identity on the top and on the bottom of it. So for instance, if we have this circuit, which is a C0 in parallel with Hadamard, we'll first do this sequentialization, obtaining a C0 with identity here and Hadamard with two identities here. And once we have this, we can consider the encoding of the C0, which is these swaps here. And then the encoding of Hadamard together with these two identities, which is this block, okay? So, okay, so we have to consider the circuit slice by slice like this, step by step, okay? So that's, okay, so it makes life a little bit harder compared to a monoidal functor, but that's the way it is, because here we have a fundamental problem, which is that this is not the same parallel composition on both sides. Okay, so for decoding, we have the same problem. So we consider also the gates in parallel with identities. And so, for instance, if we have the phase gate with one identity, we can interpret it as a phase shifter, we can interpret it as a phase gate. Now, if we have a phase shifter on 1,1 with three identities on top of it, we interpret it as a control phase, okay? So it's, and more generally, if we have plenty of identities, it's going to be a controlled phase gate. Okay, so for each generator of optical circuit, when we translate it, when we decode it into the quantum circuits, we get this multi-controlled gate. So when the generator is on the bottom part, it's easy. It's something like this. If it's on another wire, then we use other kind of control. Okay, wide control for controlling with cat 0 instead of cat 1. So, but we can always do these kind of things. Okay, so this is how the decoding works. And and for the swap, if we have a swap, we decode it as a control not. Okay, Toffoli gate in this case, which we have 8 wires, but it can be more than this, so control not. Okay, so that's the decoding. So how it works in practice. So if we start with this circuit, these quantum circuits, we have seen that we encode it into this optical circuit. And now if we decode it, each swap is going to give a control not, a Toffoli gate. And then each phase here give us a control phase gate, the beam splitters controlled X gates, and so on. So we get this big circuit. And so we see that clearly we start with this circuit, and when we apply encoding and decoding, we get another quantum circuit, but which is clearly not the same. Okay, they should be equivalent because everything is preserving the semantics, but they are not the same. Okay, so if we go back to the global picture, so here we see that if we start with a CA, we encode it into an optical circuit and we decode it. Actually, we get something C0, which is different from CA. So this is the example here. So we need, at least in our equational theory, we need at least enough equation to be able to prove that CA is actually equivalent to C0. Okay, so we need, and what we need actually is some basic properties on controlled gates. in order to be able to prove that this circuit is equivalent to this one. And by basic properties on control gate, I mean, for instance, this kind of properties. Okay, if we control an unking control with the same thing, then it's you can just replace it by this unitary transformation. So it's a simplification. Here it's a commutation property. If you anti-control and control, then you can commute the two gates and so on. So we have here some basic algebra and control gates that we need to simplify the circuit and at least do this first step due to encoding decoding. So in order to do that, we introduce a first. Okay, so here I remind you the definition of the quantum circuit, but what is important here is a way to define these control gates, because control gates, except C0, control gates are not part of the generators, so they are shortcuts. We can define control gates, multi-control gates, inductively like this. Okay, so there are several ways to define the multi-control gate. So here we choose a standard one. I think it's from Barenko et al. Paper, I think. Okay, so we have inductive definition of control gates. This is what is important. Okay. And in order to prove the basic properties I was talking about previously, like this one, or the commutation, or the fact that we can exchange two control qubits, and we get something similar, right? Or when we have a control phase, we can put the phase on the last qubit, but also on another qubit. Okay, it's a diagonal, so we can choose where to put the phase, actually. So all these basic properties can be proven using this equational theory, which is called QC0, which is made of a few equations on quantum circuits, and which is enough to prove the basic properties on control gates. So if we look at these equations, there are clearly two parts. So the top ones, so that is all but the last two, and the last two equations. So for the top ones, they are fairly standard equations. So here, double Hadamard is the identity, some basic properties here for a particular value, or the fact that you can add up the angles. You can go from when you apply X, you change the sign of the rotation, some basic properties of C0, Euler decomposition of Hadamard. Here, a little bit more involved property about control naught. Actually, this one is a CZ, so control Z. Okay, but standard equations that are used actually in several papers about circuit transformations. Okay, all these equations have been already used in some papers about circuit transformations, and we add these two equations, which are basically some basis cases, yes, of these properties. Okay, I don't want to go to too much details about these two equations. I will talk about this a little bit later. Okay, so we have this first set of equations, and thanks to these equations, we can prove basic properties. For instance, the triangle here. Okay, if we encode decode, we get something which is equivalent. Okay, so what's next? So to finish the proof, we need to be able to simulate, to mimic each step of the proof, and a step of the proof is the application of an optical transformation. So that is one of these equations. Okay, here I remind you the set of equations on optical circuits. So now we are going to consider this equation from A to E, and we'll talk about these two later on. So that's why it's we cannot really see them. And for these 5 equations, or 6 equations, because here there are 2 equations, but for A, B, C, and D, E, it turns out that the equational theory QC0 is enough to also prove this step of computation, of transformations. So here I give you an example. So for instance, if you want to apply this equation somewhere in your optical circuit, sorry, you have this phi1, phi2, so you want to do the sum. So it's an application of this equation. So notice that because of this sequentialization, when you decode what is important, this step actually consists in transforming this slice into this slice. So which means that in terms of quantum circuits, you have to prove that this controlled control gate applied followed by this controlled control gate is equal to this gate. Okay, so it's important to see that we need the context, the parallel context. So we have all these identities, which makes the equation maybe more complicated than we can expect at first sight. So it turns out that there is enough equations in QC0 to prove these kind of things. And this is the case for all these equations. And okay, so we can do this with QC0. So it remains just these two equations, F and G. And for these ones, we need extra equations, extra axioms. So for this one, it's nothing but the Euler decomposition. So what is nice is that when we translate this in a context, we get lots of controlled control gates, but we can actually get rid of these control gates and get the usual Euler decomposition. Unfortunately, for the three-wire equation here, we get this controlled version, and we don't really know how to simplify it. Okay, so that's bad news, but that's the way it is. The good news, yes. So the good news is that if you take QC0 together with these two new equations, then you can complete the picture and do all these steps, and you get a complete equational theory. Okay. Okay, so just a parenthesis here. I'm cheating a little bit because actually, since we are working with bare circuits and not a prop, you have to take into account actually each topological transformation. Okay, it's not for free. So here, actually, in the derivation, you also have to take into account the topological transformations and double check that when you translate it, you can simulate it. So, well, there are some technicalities, but I said that we'll not go to these details. Okay, so at the end of the day, this is a proof that this equational theory is complete. Okay, so I think it's my last slide. So just a remark is that once we have this equational, this Euler decomposition, we can actually slightly simplify this QC0 axiomatization. So for instance, this equation K here, actually K can be derived from the Euler decomposition. So we can derive this K, so it's not necessary anymore. And very recently, with Noé Delorme and Renaud Villemar, we proved that actually these two equations, bigger equations, can also be derived from the other ones and the Euler decomposition, and so which simplifies the axiomatization of the language. Okay, good. So, to conclude, so we have introduced this first equational theory for quantum circuits without restriction on the size of the circuit or the angles and so on. So future work, it's good to have a complete equational theory, but it would be even better if we can use it for applications like circuit optimization. So now we need strategies, we need things like this in order to really use this equational theory to simplify circuits and see if it's interesting to use this equational theory. Maybe it's better to use ZX with the standard techniques of optimizing in ZX and then extracting a circuit from this. Okay, so I don't know the answer for this. If we look at the efficiency, the complexity of a derivation, so here it turns out that there are some cases where the derivation, so from one circuit to the other, it's cannot be done in a polynomial number of steps. The reason is that the problem of deciding whether two quantum circuits are equivalent is a QMA complete, and the existence of a polynomial size derivation for all cases would imply a polynomial size certificate, so which is not possible except if QMA is in NP, but which is not expected. But can we say anything about this derivation? I don't know. Another interesting case is the Clifford plus T fragment. I think it's more complicated for Clifford plus T because you don't have this Euler decomposition, so you need really to work with Clifford plus T, and I think it's harder. Just the case of the 2-qubit case, the result by Peter Selinger and Bian shows that it's complicated when you have Clifford plus T, and maybe some connections with ZX calculus. So now we have these two. The proof has been done with independently of ZX, but maybe there are interesting connections between this equational theory and the one in ZX, for instance. Okay, so thank you for your attention. If you have any question.
Yes, Simone, thanks very much for the talk. Yeah, this is really cool stuff. I was wondering about this rule you said that couldn't be said, that you didn't find a simplification for, with so the Euler decomposition with all these controlled wires attached to it. Mm-hmm. Am I correct in understanding this is a family of rules, like one for each number of controls?
Exactly, yes.
Okay.
Yeah. It's parameterized by the number of wires here and by the angles also. So it's it's a family of equations. Mm.
And so the reason for that probably is because if you had one additional sort of free wire, you could use these constructions to decompose highly controlled gates into low controlled gates, and then you would be able to do it with like maybe a single rule. But because you have to deal with sort of these all controlled wires, like where every single wire is involved, you can't decompose them into fewer controlled things.
Exactly. Yes. So here, so that's an interesting point. You're right. So if you have an extra wire, you can decompose the controlled gate in a different way, which is much simpler. But the point is that here it's not guaranteed that we have an extra wire, and even more importantly, the way it's constructed, we know that we are producing this controlled gate by using all the possible wires, because it's by construction, by decoding, it's a gate on all, except some particular cases, like you see that here there is a free wire here, a free wire here, but except these particular gates, in general, it's really a controlled gate on all the wires. Okay, so maybe I can I can mention this. So here, maybe I didn't say it, but here we are working without ancillary qubits. Okay, it's a circuit without ancillary qubits. If you allow ancillary qubits, then you can simplify these equations. So we know how to simplify these equations if you have ancillary qubits. So actually, it's simpler when you have ancillary qubits.
Right. So you could imagine the fragment of a sort of quantum circuit with one ancilla, where like the wire is sort of guaranteed to be free in the circuit you get, and then you have a simpler rule set for this.
Mm-hmm. Yes. Yes.
That's interesting.
Could you go back to the slide with all of the equations in the box?
This one?
Yeah. So I'm not really sure how to interpret this box. So K, N, and O can be derived in QC.
Yes.
And is it? Do you think there could be possible to simplify this further, or it just N and O just seem very big equation?
I don't know. So the minimality, there is no proof of minimality. So as I said, so K, so maybe just to repeat, so QC is this QC0 augmented with these two equations here. And in this QC, we can get rid of K, N, and O. The other ones, I don't know. they are fairly simple, so I'm not sure that we can simplify. For some of them, we have, so for instance, I don't know, maybe this one. So for instance, this one, we can show that this one is necessary because essentially it does not preserve the number of C0. This is not the only one, but if you restrict to 2 qubits and you treat this one carefully, then you can show that you need this equation, for instance. So there are some equations that you can show that they are necessary, but there is no proof of minimality at the moment. So I don't know. I don't know.
Follow up to that. Does this mean that every circuit in we know how to simulate every quantum circuit in the circuit model with a linear optical diagram, with linear optical computation?
So here, so this construction gives you a way to transform any quantum circuit into an optical circuit. Yes, but be aware that the number of wires is exponential in the number of qubits. Okay, so it's probably not an efficient way to simulate quantum circuits. So it's useful for the proof, but in practice, it's probably not the best thing to do. Okay, to do this encoding for simulation or for computing the matrix, or I don't know. I think it's somehow similar to computing the matrix because it's exponential.
How far do you get in the opposite direction of taking any linear optical circuit and taking those generators and writing them as circuits?
So we have a decoding here. So there is we transform optical circuits into quantum circuits. So there are some restrictions because we assume, for instance, that the number of wires is a power of 2. Because by construction, the encoding is, we only decode circuits which have been encoded. So it means that the number of wires is a power of 2. Otherwise, we don't know how to do this because we don't have the same dimension on both sides. So for this family of circuits that is with the restriction that it's polarization preserving single photon and that we have the generators we consider with the number of wires and so on. For this fragment, we know how to go from optical circuits to quantum circuits. For other fragments, I don't know. I don't know. I think it's I think there is a, so for instance, if you consider the polarization, it means that you are going to add, for instance, an extra qubit when you decode, when you go from optical circuits to quantum circuits. You can probably add this extra qubit encoding the polarization and then do a decoding in a similar way, probably. And if you have several photons, then it's much more complicated because it's a different semantics.
Assuming that the reason why you get this exponential blow up when you go to optical circuits in this case is because it's the single photon case. So if you had a model where you had lots of photons, and I'm assuming that you can efficiently simulate quantum circuits.
Okay, so if you use several photons, then you then there is this interesting question of how to simulate quantum circuits using optical circuits. And there is this KLM, for instance, construction. There are other ways to simulate. If you really have lots of photons, you can do continuous variables. But the point is that all these simulations are non-deterministic. So which means that when you simulate a unitary transformation, it's you have some probability of success, which is not 1 in general. Well, yes, and yeah, I don't know if well, I don't know more than this, but this question has been investigated already, and so there are some this encoding, but yeah.
Yeah, I don't think that it would be straightforward because as soon as you have more than one photon, you also have the possibility of more than one photon being in the same mode. And so there's a direct mapping from that picture to a circuit on qubits.
Yes. Yes. Yeah. Yeah. That's the point. Yes. Yes, that's why it's non-deterministic. That's when you have two photons, you may say that, okay, one photon is encoding one qubit and the other one another qubit, but if at some point they are on the same wire at the same, and they are indistinguishable, then it's in general, you are lost in this case. And you need to measure and exclude this case somehow, post-selection.
Simon, have you taken a look? I mean, many of these rules look, they've got natural corresponding rules in ZX, and including, for example, E would look like the Hopf law, which is not something we take as a primitive rule anymore, but it's certainly something well understood. Do you get any interesting structures from the ones that are not obviously corresponding to simple rules in ZX? If you ZXify them, do you get any structures that sort of pop out as being interesting somehow?
Okay, good point. So yes, so this triple C naught is related to bialgebra, I think. This one is a Hopf flow, simplifying C naught. So all these things are well known. So for instance, with chatting with Renaud Villemar, he said that I think N, equation N, is closely related to one of the equations we had to have the completeness of the ZX calculus. So yeah. So for instance,
isn't N saying that a ZZ exponential commutes with an X exponential, XX exponential? Because you first have like a ZZ phase gadget, then you put a Hadamard, so you have an XX phase gadget, and then you commute these two. But then you also have this additional phase on top, and it looks like these phases have to be the same and opposite in these cases.
So it's clearly a commutation property. So I think I can see it in terms of controlled operation, but probably in terms of phase gadgets. This is what you mean?
Yeah.
Probably. So phase gadget is going to be so when you have a structure like this one without this X rotation, it commutes with the control, right? You can push it here.
Yeah.
And what it remains is a phase gadget, is a X phase gadget. So here you can do something similar. And so yes, so at the end of the day, it's with Hadamard, it's probably changing the colors. And yeah, so it's probably something, as you said, yeah, commutation.
Yeah, so it's saying like for specific angles, there's an X rotation followed by an XX Pauli gadget that commutes with an XZ Pauli gadget followed by a Z rotation, as far as I can tell, which obviously is angle dependent because XX and XZ won't generally commute.
Yeah.
Okay. So here there is no connection between theta and theta prime. What is important is that here you have theta and minus theta, and here theta and theta prime. So yeah, I don't know, but probably, yeah, you can probably.
Yeah. So I think if you were to write these as phase gadgets and then you translate the phase gadgets into H boxes, so into a controlled phase gates, I think the additional phase you have in your other qubit cancels one of the phases and makes the gate be trivial on one of the qubits, makes that control into like just a control where nothing else is happening. So I think if you translate it into ZH, this rule might become obvious, but then you need a translation between like a phase gadget and an H box, which is like a more complicated family of rules. But I think then this rule might become more obvious, but I need to actually write it out.
Yeah. 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 Interesting. Yeah. So yeah, we know that in so for instance in ZH, all the axioms are meaningful in terms of so there is a nice interpretation. So yeah, it would be interesting to see how we can interpret how we can ZH interpret these equations. It would be interesting. Yeah. Yeah.
I think you can also.
Well,
oh, sorry.
Nope.
I think you can also translate equation O into something that is cleaner if you write it in ZX, because you'll get a lot of 6 cycles of green, red, green, red, green, red.
Mm-hmm. Yes, yeah. Okay, yes, yeah. Okay, tried a little bit to yeah. Okay, yes. So in ZX, maybe if you allow to go outside of the quantum circuits, outside of the circuit-like diagrams, then maybe you have a fairly simple proof of O. If you want to keep inside this to stay inside this circuit-like diagrams, well, there is a way because we have it, but I would not say that it's trivial, but yeah. Or maybe there is a simpler proof than the one we know. But yeah.
So O is saying that the circuit on the left is self-adjoint, right? Because the right-hand side is just a flipped version of the left-hand side. Not the transpose, not self-adjoint. Yeah.
Okay, yes, there are some subtleties with the sign, I think, when you do this. Yes, yeah. It's either the transpose or self-adjoint, yeah.
Just
clearly some symmetries, yes.
There's one question about minimality, because I see you have the HH cancellation, rule A, and then you have this Euler decomposition of the Hadamard. It feels like one of these two should be superfluous, especially with consideration that you have the general Euler decomposition rule.
Okay, so the point is that here, from the beginning, we assume that that the generators are H and P and phase gate. So R, the X rotation is a shortcut. So it means that.
Oh, I see. Yeah.
So here so actually it's a PHP HP, something like this.
Right.
And so at some point you need a double H equals to identity because of this definition. So
I see. So in Renault's completeness paper for universal ZX with a Euler decomposition rule, he gives us two different versions. He has a regular Euler decomposition rule, and then he has the one which has some Hadamards in there, and that allows him to get rid of some rules. Like Renault, I think, is in the chat as well. So please tell me if I'm wrong. Could you use this modified Euler decomposition rule to maybe get rid of the one of the rules here?
Maybe, I don't know. I don't know. Maybe. Is it completely equivalent? Yeah, it is equivalent. Yeah, I don't know. Maybe. But Euler decomposition is well, it's a standard equation, so I think it's not really the one that I want to remove from the axiomatization, but yeah, but maybe it's a way to decrease the number of equations.
So if there aren't any more questions, then let's thank our speaker again. Great talk. And as always, let me know if you have any work you want to give a talk about. Thanks.